Today we're just going to be talking about thermodynamics. The whole unit includes thermodynamics, exothermic, and endothermic. But today we're going to be talking about thermodynamics, a little bit about endothermic and exothermic thrown in there, and a little bit of energy. All right, so we're going to start by talking about the first law of thermodynamics. And the first law of thermodynamics says that energy can be converted from one form to another, but cannot be destroyed. It can be converted from one form to another, but it cannot be destroyed. So converting from one form to another might be, for example, changing from chemical energy to chemical energy to electrical energy. So that would be like a battery. Or potential energy to chemical energy. So that would be, for example, a chemical reaction, because the chemical energy is stored in the bonds, in the compounds, and then a reaction would break and release that chemical energy and then reform it in new compounds. And so that energy would be converted into chemical energy from the bonds. Now, I want to stop here for a minute, and we're going to go into something that's a little bit overarching umbrella on this unit. Okay? So it's a very big, simplistic concept that's going to come up over and over and over in this unit. So I'm going to start, and it's not really very conducive to being on a video. So for those of you who are watching the video, you might want to just sort of sit back and relax, and I'll kind of do my best to make it video worthy, but it's more of one of those things where I'm kind of up dancing around the classroom, but I'm not going to actually be able to do that because it's on a video. So just bear with me, because I'm having to switch modes here. Okay, so imagine, I'm going to do this here. Here we go. Imagine if me, was a cube of iron. I know, weird. So, all right, I am a cube of iron, and I'm going to go so far as to say, for this discussion, this is me. This voice that you hear on the video, Miss Paxton, am now a cube of iron. So from now on, when I say I and me, I am now speaking as a cube of iron. So in your brain, you're getting a little picture of a cube of iron without curly hair, just a cube of iron. Okay, so I get put on a burner, all right, and I am going to, because I'm not acting this out anymore, so I'm writing things down so that I'm keeping my audience engaged. All right, and so I am going to go from, let's say, 0 degrees Celsius to 150 degrees Celsius because I'm sitting on a burner. All right, now that means I have gained energy. And I am now going to be brought into the classroom on a tray, and I am going to be put down on the table. So what happens to my temperature now? Yeah, good. So it's going to drop. I'm going to drop in temperature, and I am going to lose energy. As this little block of iron, I am going to lose energy. So let's move back up here. So for our discussion, all right, I am going to be considered a system. A system. This block of iron is considered a system. And when we're looking at what's happening with this block of iron, me, when we're looking at what's happening to me, we're looking only at me. We're only looking at this block of iron. Well, the block of iron got put on the heater, and the block of iron gained energy, and the temperature of the block of iron went up and it gained energy. And then when we brought it into the classroom, the block of iron's temperature went down and the block of iron lost energy. So we're looking at it as a specific system. So now what I want you to think about is, when we think about the law of conservation of energy, and we think about the first law of thermodynamics, we're also talking about two other things. We're talking about the universe. And the universe is equal to the system, me, plus the surroundings. And the surroundings are considered to be everything in the universe, including Saturn and Neptune, everything in the universe except what? Me. Except me. Because I am the system. We're looking at the system. We're looking at that little cube of iron that gained energy and then was brought in and set down on a tray on the table, and then it lost energy. Where did it lose energy to? The surroundings. Right? So the system, me, the block of cube, gained energy, then lost energy to what? The surroundings. And we could even go so far as to say, well, how much energy did I lose? Well, we don't really have units. We don't know the words for units. So I'm going to give you one. Let's just call it, I don't know, marshmallows. And let's just say that I, the block of energy, I lost, I don't know, I lost 5 marshmallows. How many marshmallows did my surroundings gain? 5. 5 marshmallows. Now, a lot just happened in this little scenario that I gave you about this block of energy. A whole lot just happened. So let's recap a little bit. Very simple, kind of a silly example, but demonstrates a huge amount of information. First of all, this idea that what you're looking at, whether it's a reaction or a block of iron or an entire huge pharmaceutical reaction that's really gigantic, it doesn't matter. Whatever you're looking at is called what? Whatever you're looking at is the system. The system. And everything else is the surroundings. And the two of them add together to make the universe. And this is huge in your class next year in physics. Because whenever you're talking about energy, there's only energy in the surroundings and energy in the system. And they add together to make the energy in the universe. The next thing that's important to note is that when we're talking about energy being lost or gained, we're only talking about looking at a small piece of it at a time. So when I'm looking at me, when I'm looking at myself, or you're looking at me, you're only talking about whether I gain or lose energy. And if I lose energy and you touch that block of iron, it will feel hot because it is losing energy. And when something loses energy, it's called exothermic. And so when a system, any system, loses energy, it's called exothermic, and it is negative. And the reason it's negative is because the system, the thing that you're looking at, is losing energy. That's why it's negative, because when we isolate it and we look at only that part of it, it's losing energy. Next, we're going to look at what happens to that energy. That energy went over to the surroundings, and so the surroundings gained energy. And since I can isolate it and look only at the surroundings, and it is gaining energy, we call that endothermic. So by isolating each piece of that, we look and see, is it gaining energy, endo, or losing energy, exo? And then the big umbrella thing that's happening here is when I add the energy lost by the system and the energy gained by the surroundings, I get 0. And the reason that happens is because the law of conservation says what happens to the system, the opposite of that happens to the surrounding. So energy, negative energy. Whatever it is that's happening to the system, the negative of that is happening to the surroundings. So if the system is losing 5, the surroundings is gaining 5. If the system is gaining 5, the surroundings is losing 5. So there are a lot we just talked about, okay? This is going to come up over and over and over again in this chapter, and then over and over and over again next year, and it's going to be on your final exam from the county. I can guarantee it, okay? Questions? All right, let's move on. We'll talk about it again. I can guarantee it. Let's move on. So let's talk about heat. Heat is not the same as temperature. We know that temperature is the average kinetic energy in the molecules in a substance. This is not that. Heat is enthalpy. It's described as enthalpy. And enthalpy is energy that's being transferred from one substance to another. Now, we have a phrase for heat. We have a symbol for heat. It's delta H. Now, that delta means change in. So this would be change in enthalpy. And you find the change in by the final minus the initial. So in other words, this is going to be the final enthalpy minus the initial enthalpy. Or change in temperature would be the final temperature minus the initial temperature. Now, enthalpy can be negative for exothermic or when heat is being released, or it can be positive for endothermic when heat is being absorbed. Now, on your periodic table, you're going to write these 3 things because we need units for heat, right? You can't just have heat and then not have units. You need units. So here are units, and we're going to go over this again and again and again, but you're going to want to put these on your periodic table. The unit calorie is defined as the amount of energy to raise 1 gram of water 1 degree Celsius. And I'm going to go over that in just a minute. And then, as a conversion, we have 1 calorie is equal to 4.184 joules. So joules is really the unit of energy that we use more often. We use joules more often than we use calories. So they're smaller and they're more precise because 1 calorie is equal to 4 joules. So, they're a little bit smaller, so they're more precise. So we use joules more than we use calories. Lastly, 1 calorie with a capital C is equal to a nutritional calorie, and that is 1,000 of the calories that we use in the class. 1,000 of them. So you're going to want all 3 of these put on your periodic table. Okay, so I'm going to give you a minute to do that now. Okay, so to further define 1 calorie, imagine if I had like a little cup here, and in that little cup, it had 1 milliliter of water, which is equal to 1 gram. And I added enough energy to raise that little cup of water from 5 degrees Celsius to 6 degrees Celsius. The amount of energy that it took to raise this little 1 milliliter of water from 5 degrees Celsius to 6 degrees Celsius, that would be one calorie. That's how much energy it would take to raise 1 milliliter of water from 5 to 6 degrees Celsius. That's a calorie. Okay? So that's what that means.
Is that only with water?
Only with water. Excellent. Yes. So Rachel just asked, is that only with water? And the answer is yes. Every substance has its own specific heat. And so if I open up to page 516 here, and I show you the bottom of page 516, what you'll see, where is it? There it is. So if I show you page 516, here's a whole list of the specific heats for a whole bunch of substances, and they're all different. Even ice, and here's water liquid, water solid, and water gas, they all have different specific heats, and the reason is because the amount of energy to raise 1 gram of the substance 1 degree Celsius is different for lots of different substances, and we're just about to talk about that on the next slide. So 1 calorie is the amount of energy to raise 1 gram of water 1 degree Celsius, which then of course would be 4.184 joules, because that is equal to 1 calorie. But that's more than enough energy for solid water, for ice, and it's way more than enough energy for magnesium, right? You don't need that much. So let's see. So specific heat in particular, there we go. Specific heat has calculations that you can use, and there's the table, page 2, table 2, number 5, page 516. Okay, that's on your assignment sheet already. And they calculate things like how much energy is needed to heat or cool a sample of a substance, any substance. Doesn't have to be water. And you use a constant for each substance. All different substances have their own specific heat. So specific heat, which uses the letter C, all right, is the amount of energy in joules or calories that's needed to raise 1 gram of the substance 1 degree Celsius. So if it's iron, then iron's specific heat is the amount of energy it takes to raise 1 degree Celsius, 1 gram of iron, 1 degree Celsius. And it's going to be different than raising 1 gram of water 1 degree Celsius, all right? So you look them up in the table. If on a test you needed that, I would either give you the table or I would give you the number, because there's no way for you to know it. And certainly you don't have to memorize it. But in the next slide, you're going to put the water one on your periodic table. So you have it, okay? All right, next. There's a formula that we use for these. It's called the MCAT formula, all right? And there's a formula that we use for all of these calculations. So here it is. Q equals the mass in grams times C, and there's C right here, the specific heat, all right? And that's going to be either in joules per gram degree Celsius or calories per gram degree Celsius times, I'm going to pull out a little bit here, times delta T, which is going to be TF minus TI, and that's going to be in degrees Celsius. Specific heat is going to be either in joules per gram degrees Celsius, or it's going to be in calories per gram degrees Celsius. Those are the units of specific heat, right? Because you can either have joules or calories And it depends on what you're working in, and it depends, the number would depend on whatever the substance is. Now, Q is going to be the amount of energy, and if it's positive, that means endothermic, right? Because if it's positive, remember we're looking at the system, that means the system gained energy, endothermic. If it's negative, that means the system lost energy, exothermic. Oh, I guess they're... Okay, so this is going to be, the units of specific heat can either be joules per gram degree Celsius or calories per gram degree Celsius, and that's going to be the units for specific heat. Yeah, Aaron. So that is going to be for the delta T from over here. The delta means change in. Its standard format is final minus initial. Okay? And that's in physics, that's in everything. That's even in, like, if you change your graduated cylinder volume, it's going to be change in volume, and it's going to be TF minus VF minus VI. All right? Okay. All right, yeah. Yep, delta T is change in temperature, final temperature minus initial temperature. All right, and you're going to end up with Q, and it's going to tell you whether it's an endothermic or an exothermic. And how would you know? Because let's say you're raising your temperature from 50 to 100 degrees. So that would be 100 minus 50. So that's going to be a positive. So that means this is going to be endothermic. Positive Q. But what if you're going from 100 degrees to 50? That's going to be 50 minus 100. So that's going to be negative 50. So your Q will be negative exothermic because you're cooling down, so you're giving off energy. Okay? Let's take a look. Here is your specific heat problem. Now, I'd like you to write this problem down, write down the formula, and then the highlighted portion here, I'd like you to, this is see this? Specific heat of water, 4.184 joules per gram degree Celsius, or 1.00 calories per gram degree Celsius. Those need to go on your periodic table. So I'm giving you time to put them on your periodic table, those two specific heats of water, all right? And then I'm going to do this problem for you, and then we have a sample problem for you to do, okay? So these two are the specific heats of water, and you can notice the units. I'll zoom in a little bit. You can notice the units. The units are joules per gram degrees Celsius or calories per gram degrees Celsius. So let's do this problem. Ready? So first, notice I have the MCAT formula here. Q is going to be the amount of heat that is either absorbed or released. So let's start. Q equals the mass, 34.4 grams. So here's my mass. Here's my temperature, right? So times my temperature, because I'm doing Q equals MCAT. So here's my specific heat, and here's my delta T, right? So the next is going to be my specific heat. So 4.184 joules per gram degree Celsius. That's my specific heat of water. Okay? Next, I'm going to use my change in temperature, which is going to be 78 final, 0.8, minus initial, 25.0, and then degrees Celsius. Next, I'm going to run my math. All I have to do is multiply across. Oh, before I do that, I want to do my units. I can cross out my grams, I can cross out my degrees Celsius, and I'm left with joules, which is great because joules is a unit of energy. So now I run my math, which is great because it's nice and easy, straight across multiplication. And I get 3 digits, 7.74 times 10 to the third, and my unit that's remaining is joules. Now, yeah, Vicki. Most often we use joules. So you only use calories when you're asked. Yes. Yeah, so the answer to that is pretty much joules. Okay. So now the next question is, was this energy absorbed or was it released? So remember, we are the system. Okay, so the system is positive energy. Well, does that make sense? Well, we went from 25 degrees to 78. Yes, we must have gained energy because our temperature went up, right? So in order to do that, the temperature increased, so the system gained energy. Did it? It did. This is positive. So the temperature went up, we gained energy, which endothermic or exothermic? Endothermic. So all of this works. Endothermic. All of this plays out perfectly. Temperature increased. Energy was increased, right? Positive answer, endothermic. See how that works? Are there any questions? Okay, let's do a problem. Here we go. Your problem, ready? The temperature of a block of iron changed from 50.4 degrees Celsius to 25.0 degrees Celsius. The block is 10.0 grams. Yeah, so you can pretend this is me. All right, so the block is 10 grams, 10.0 grams, and 114 joules of energy is released. What is the specific heat? Right, I know. What's the question? What is the specific heat? So what variable are we looking for? Yeah, what is the specific heat of iron? So this is going to be different than the 4.184 because that is the specific heat of water. We're looking for the specific heat of iron, so it's not going to be 4.184. Yeah.
So instead of putting Q equals, would you put 114?
No, yes, that's exactly right. So Aaron says, so for instead of Q, you're going to put 114. Right, because essentially this number here is Q. Right, that's the number that's released. That's Q, yeah. All right, so you're going to now write out your formula and solve for Q, okay? And solve for C, that's right, specific heat. Now also I'm going to tell you that when you do your division, your algebraic work, your units should work out pretty nicely, okay? This first line is your original line, final minus initial. All right, your final temperature minus initial temperature. Then, to get your C alone, you're going to divide out. So I divided both sides by my mass and my temperature, which got my specific heat by itself. But not only that, when I did that, I got grams and degrees Celsius. So my final units were joules per gram degrees Celsius, which is what I want for my specific heat. And then when I divided this out, I got 0.449, which is in fact the specific heat of iron. Okay, your assignment is in your textbook tonight, and I've put it up on Canvas.